So, I wanted to do a live broadcast. My computer hard drive crashed, but luckily I use a disaster recovery policy that I use at home, just like I implement at work. But I got everything back up and running. Open Muscle and the Lask system works surprisingly well. It's pretty robust, even throwing some arm twists into it. It has a lot of promise. Um, One of the difficulties is if it's going to be applied as a prosthetic sensor, there's going to be things that you're going to run into, like the muscles are not connected to a tendons, and if the muscles are moved into a different location, if there's more fat tissue in between the open muscle sensor and the muscle itself, atrophy. Lots of factors could actually adjust how accurate it can detect. But the thing is that with 4 minutes of training data, you can get an insane accuracy. So since it's able to follow the curve, you're going to have to switch the output into a Boolean fashion, or into you're going to have to classify it maybe just three different outputs, and you can get an insane accuracy with the current setup. And there's little to no filtering, but that just shows how good random forest regressors are at filtering out noise. And there's a lot of noise in the system, and I've even moved the bracelet in one of my tests, and it still just nailed the accuracy, the calculating which finger I was moving. I even used it with the last turned off. But hey, let me see if I can just hop into the data. I should probably I did not. Even OBS Studio is kind of messed up for me, so I apologize. But since EML, they reached out to me and they just said that they're interested in the project because they believe it could help people. But this data right here has everything from the sensors and the predictions, and it's just kind of interesting to look at. These are loaded onto GitHub, but just to illustrate kind of what's going on, here is of course, the prediction is the brown and the green is the real, I believe, in this example. And it still kind of follows it. So if you put your threshold right around here, which would be 4,000, you could accurately detect this. Some of these smaller humps are interesting because the nature of uh, how I'm capturing the data. I won't go into that, but this is what it looks like. It's just super neat to see it. And not only can it run um, after the fact, which is what this is. It wasn't done live, but we can actually run it live. So I kind of wanted to show you that. And I have hundreds of hours of all this stuff. Here's what the packet looks like from January, and that's from this data set. Whoop. Let me see if I can. It doesn't like how big this file is. But let me open up my GitHub folder, and then we can kind of hop into the demo. Because I wanted to show you guys kind of what that looked like. And I'm not monitoring my session very much. When it comes to being live, I just didn't have much hard drive space. One of my hard drives broke. And hopefully, this is streaming properly. Let me just run a test. I don't think my YouTube Creator Studio is working. I should get a notification. Yeah. It's live. It's live. Sorry about that. So what I did in the demo folder in Open Muscle, I tried to make a demo folder so you could train your own. I also uploaded the model to Hugging Face, and let me just add my camera real quick. Please forgive me, guys. Again, I have hundreds of hours recorded, and I was trying to just show you guys Elgato Facecam. I really enjoy the Elgato Facecam. But yeah, so what I did here is I pretty much have a couple extra files because I was wanting to look at this. The predictions with OM and Lask, those are pretty neat. I need to delete these ones. So if you want to train it, what I did is train model time. You'll see this in the Wikipedia for the Open Muscle. It's not Wikipedia, the wiki of the GitHub for Open Muscle. You'll find this train model time. And if you open this up, what you're going to see is it just runs the calculation, and it trains the model based off of the file. Is Capture 11. Capture 11 is one of the more recent captures, and what's nice about it is that I had the open muscle bracelet on the same spot, and so capture 11 and capture 12 were taken one after the other. Capture 11 was a little bit longer. Both of these used random finger curls, as I'm calling them, or finger presses with the LASK system. And the same thing for capture 12, but capture 12 was just used to test it live. So you can download the model, but if you just run it on your computer, it doesn't take very long. I'll show you. I'm going to run the model. And of course, I have Hello World on there because what program would not be complete without Hello World? But it just tells me that that loads after it imports, I believe. Let's take a look at it. So yeah, so it imported scikit-learn, and it's going to split the data into the 80-20 here. And I'm using 13 parameters in and 5 parameters out. I like adding the time domain because you can actually calculate the velocity and send some other numbers into the random forest regressor, and you'll get predictable finger movements with the same sensor system. But with the raw time data, it's able to calculate the slope and any other thing that you could think to throw at it. So I have not seen where it actually memorized anything, and because of the random types of gestures that I've sent to it, and there it's completed while I was talking like a fool here. So it says it has a mean absolute error rate of 29. And again, the values for the LASK system, I think for this one, range between 5,000 and 5,300. So we have about 300 different levels of pressure detection, whatever we want to call them. And so having 29 off, then we have pretty much, we can split it up into about 10 different increments if we want, but we want a higher accuracy. So if we reduced it to a Boolean value, I didn't go into that because this is more a proof of concept. It works so well, I believe that it should spur some innovation in the field. So I've already made capture 11, but just so you guys know, I have the filter here. The filter here is an algorithm that I wrote to actually match the pairs, because this data is being sent over UDP from the operating system that I designed for both the open muscle and the LASK system. But it just sends a processor tick, some other things. It lines them up. So that way the machine learning model has enough information to glean discernible finger movements. So back to the training. So our training's done. We can close this file. I am going to make a one-click run, but again, I'm just more looking for people to help me with this project. I'm not looking for other people to necessarily... If you know what you're doing, you should be able to tease apart this information relatively quickly. But I do want to also try to explain it. But my time is limited, so that's why I'm also not editing this video. I'm just doing it live. So now that we did train model time, we can go ahead and do demo time, and then I don't want to do the live. So demo hand time, and again, that's in the wiki, the documentation. So what this will do is this will run the graphic user interface, and so if I run that, it should open Pygame, which Pygame is nice because it was quick for this example. Awesome. And now I'm going to use the virtual sensor transmitter. So what that does is if you don't have a LASK system or open muscle band, you can go ahead and send the dummy data over to it. So this is going to take the packet capture 12 that I talked about earlier. So both of those were recorded in one stint. I didn't move the bracelet on my arm. The video that I posted, I think second to last, before some of the stable diffusion stuff, I also live recorded me and seeing the outputs through this Pygame interface. But the Pygame interface does not inherently record what's going on because it's doing a lot of other calculations. So when I run this virtual transmitter, it is just straight up throwing the exact text file that's initially recorded when you record these. So it sends it over UDP to yourself. And my good friend Harry, he designed the hand because I literally had no time. And this is what you see. So the yellow is actually the predictions, and the cyan is the actual value from the last. Here is a false positive, and you'll see a couple of these, but they're surprisingly low. Also, the nature of how I'm sending this data into the machine learning model, it is a little bit more sparse because I'm having to process it. So there's a lot of refinements I need to have. But the fact that the yellow line even is close and even jumps up when the blue line does on the top four is literally amazing to me. It shows how efficient artificial neural networks can be at solving problems that have a direct correlation to the input. Now, this data was only about 4 minutes of training, and it also, the sensor system was tighter than normal. And so I found the best predictions, and there you go. See, even multiple finger movements it was able to detect. The best designs are when you or the best captures are when it's not so tight around your arm. And I do have two versions. So I have the version that is the more effective, and that uses the clevis pins here and springs. It's very difficult to reduce the friction in the system, and the ones that use foam, actually it does work pretty well, but I have a lot of refinement to do. And the packet capture ends, so I'm going to just resend it. So this is kind of how you can use the data files located inside of the GitHub to run and see it predict live. So these predictions, I'm not sure the actual calculation, but if you watch this video recording and if you count the number of dashes in the yellow line, it will tell you exactly how many predictions per second. I estimated that to be in between 5 and 15. But yeah, it's really exciting stuff. Working on a whole bunch of improvements, working at talking with people. People are actually kind of getting interested about it. I was excited that it produced the results, and honestly, I was expecting it to take longer because I thought I would need a lot more time. But random forest regressors are really good at getting rid of the noise. This is not a very good example. You'll see that there's a lot of noise in those predictions there, but it's not always the case. And I kind of, if you watch my channel at all, I try to show both the good and the bad because I don't know, it's just transparent that way. But it's just super surprising being able to strap this onto one of my friend's arms and to test it. And just to show it live is pretty neat. I have another demo for it coming up this Wednesday. But yeah, let me just go through the process of training your own model. So if you go to github.com/turftax/open muscle description, link should be in the description. And you'll want to open up the file after you, depends on how you load it, but if you just download it, you'd have to unzip it, however that is, and then you want to go to train model time, which you'll find those instructions on the wiki. You run that, and that will actually train the model based off of a file in the data captures, which is data capture underscore 11. And I've already converted the file for you to CSV, but if you wanted to load your own data, if you have your own one, you would use the sensor data filter. The sensor data filter live, not sure why I named it live. I'll have to look at the code. But yeah, it's mostly me. I've written all the code myself. There was a couple of lines that ChatGPT helped me with, especially when it came to parsing the outputs from the predictions that I asked. But the most part, it was me. So when you solely program on something, there's a funny saying. In what is it in computer engineering and programming? Back then, only two people knew how the program worked, God and me. Now only one person knows. And of course, I don't know how it works. I do know because I wrote it, but it's one of those funny sayings that if you do a lot of programming. I like Python because Python is pretty easy to use. Rapid changes could be done without actually compiling the code. That's why I also like MicroPython for my microcontrollers. I've even written a MicroPython over-the-air update module called UGit. That's been pretty fun to write. I love networking. I love solving the problem, like filtering the data. So that part has been amazing. But the fact that this could potentially help people, or at least make this information more readily available to any other hobbyist that wants to improve on the design, I have the designs for the next version that actually has a more scalable solution for the sensors. These are very cumbersome to make, but they're good for a proof of concept. I'm drafting up a pseudo science paper. I'm drafting up, it's not scientific. I'm just trying to gather the information that I collected in an intelligible form to point people in the right direction. Again, this is just what I do on my free time. I have a passion for helping people, and I think that that's what's so neat about artificial intelligence is that you can ask it questions. It's like having 10 experts next to you. You know, they'll give you some wrong errors, but if you ask it some interesting questions. I asked it specifically. I have 12 or 13 dimensional problem that has five outputs, right? So it's a conversation about how to apply the best artificial neural network to it and some teasing. And the design itself, I enjoyed having radial symmetry. And one of the biggest problems with one of the biggest problems with prosthetic sensors that I have heard of is that the accuracy, number one. Two is sensor placement. Three is latency. Four is comfortability. That's probably like number one. They're not in any order. They're just the ones that are coming off the top of my head. I aimed for open muscle to solve the sensor placement with just increasing the sensor density. Have more sensors, then you don't have to worry as much about the placement. Also, rotational symmetry because I wanted to try some unique machine learning techniques that I have in my head that I wanted to try to implement. And that is super fun. Also, the latency because I'm getting this signal at about 100 samples per second per sensor. Overall, 1,200 samples per second, of course, for one bracelet, 100 each. I'm able to parse that data and filter it and send it in to the model that then predicts it. Right now, the model that I'm using is about 270 megabytes. Let's take a look at that, actually. Demo, this one was January 23. Oh yeah, the January 23 is giant, but this is 163 megabytes. So this is only 163 megabytes. I'm able to get 5 to 15 predictions per second. The latency is not too terribly bad. What's interesting is that by design, I tried to have it be a live prediction device. So it put extra constraints on the designing process, which proved to be fruitful in the end when I finally plugged into machine learning. I did it very blind. I designed this whole thing knowing that I wanted to get to a certain point, but I had to have each of the pieces, right? If I didn't have the last system, I couldn't apply meaningful labels. If I didn't have a bracelet system that was modular, that I could swap out the type of sensors that I was using, I also had to learn how to make the PCBs. It was an interesting process, but overall, um, just trying to gain awareness that I think that artificial neural networks and deep learning and the technology that AI is bringing can really help humanity out. And I just think that it's very, very cool. I do not know what the future holds, but I'm very interested in using it for good and also protection. I'm in the cybersecurity industry, so I often have to deal with cybersecurity threats and regulatory systems that's kind of commonplace. So I'm also designing this with those things in mind, so that way it could be used in a hospital setting with the regulatory compliance. Yeah, there's a lot of factors. One of the things is that AGI is, of course, scary. But what's even more scary is just the fact that a lot of these natural language processing AIs or large language models, they can be used for bad. And so, well, I think of it with a security sense in mind in some of my red team days. Um, just yeah, it's scary, but at the same time it's easy to get overwhelmed, but that's why it was a fun project to work on. It's not just a project I'm going to carry through even further, but there's a lot of people joining, so I just want to encourage anyone, if this is something that you're interested in helping, please join. Go to the website openmuscle.org, follow me on social media. I enjoy the community of open source and open hardware. I think it's beautiful when people can work together and share information freely. I think it can actually increase the help that you give to people quicker. But if you do something like this for assistive technologies, you can't just leave it alone once it's done. You can't just invent something and say, I'm done, problem solved, move on. you also have to continually support it, which I think a lot of people forget. Like they're like, if you don't actively keep something up to date, it will eventually just crumble. It's not like, oh, you invented something, the code works once, it will always work. There's actually a lot of time and effort that goes into it, and so it needs to have community adoption if it's going to use. And I was very fearful early on that somehow I messed up the machine learning. It was memorizing part of the signals, so I did kind of delay this video until I was sure that yes, I'm getting the same results. I've tested it with different sensors. I've had it not work and broke it on purpose, and it broke. I've had it work, and sometimes work, and it didn't work when I thought it should. And it turned out that I was actually using the model that I had trained on a different sensor itself. But it was ups and downs. It was actually pretty tough. But also, it was a little lonely because um, I was mostly doing this by myself. Had a lot of questions. I couldn't find the answer, but ChatGPT, especially 4.0 or ChatGPT 4, 3.5 Turbo, I've been using with the API calls and doing some grunt work for me. But it's just a very beautiful system. I feel more productive now that I can sit down and with AI be able to churn out more ideas and to maybe potentially make a bigger impact. So I think the ramifications of releasing the large language models to the public is can be positive too. Just kind of like any powerful tool, right? If the tool has power, it can be used both for good and bad. And my personal measure of good and bad is good is increasing joy and decreasing suffering, and bad would be the opposite. But with that, I'll leave you with the same sign off that I normally do. I just want to thank everyone that has encouraged me along the way. A special shout out to Ultimate Robotics. Special shout out to Sensi ML for letting me use their software and volunteering their time to help me with the machine learning process. Um, I will definitely reach out to them again, and anyone that has supported me along the way just by saying, "Hey, keep up the good work." I mean, that stuff that really helps me out a lot. It gives me energy because when you are potentially doing something positive, I feel like I can pour my heart into it. I do have a main job, so this is what I do on the side. So keep that with a grain of salt. Spelling is not my specialty. I'm more of just yeah, I'm a doer, whatever. So with I'm gonna leave you guys off with what I usually say, which is let's see if we can make a